Okay, so my plan is to finish talking about the visual cortex today. That actually puts us a little bit behind because we need to get this information into a form of seeing objects and perceiving faces and moving that through the brain before we can actually talk about perceiving objects and scenes. So I'm going to come to this mind-body problem that I typically do right after talking about physiology and then come back to a couple of times. I'm realizing that we're pretty behind, or I was trying to put that review of concepts so that we've gone over this problem and maybe even come to it a couple times, but we're going to review some concepts on Monday where you all are going to explain them to each other, and there's going to be at least one kind of more philosophical group that is going to be addressing the mind-body problem. So if you're really interested in this question and this problem, and you're watching this on Friday, you might email me and let me know, hey, I want to be in this group. Otherwise, I'm going to randomly place you all into groups. But so the mind-body problem is really the question of how does the mind and thought and perception and all of that relate to the body and the brain and the real physical aspects of our mental lives. So how do these physical properties like nerve impulses or what made up of, right, sodium ions and potassium ions flowing across a membrane, how do they transform into the richness of perceptual experience? I'm going to walk through this in a number of ways, and I really want you to think about the question and think about right now in the visual cortex, are we there? And again, I feel like I'm a little bit early, I guess, with this review of concepts because we're behind, but we're going to come back to this when we really start to put the information back together. We've really pulled it apart into features, and we want to put it back together into what those features make up, right? So my table over here, or somebody's face, or the television set, or whatever. But this mind-body problem is really often referred to as the hard problem of consciousness, coming from David Chalmers. There's an easy problem of consciousness, which is how do these physiological responses correlate with experience? And most of the research, it's really looking at correlations. We're looking at what are people perceiving, and then we're measuring their brain activity, and that's really the gold star of that kind of triad of whether I get a psychophysical measure, a physiological 1, or a physiological 2. I want the physiological 2, right? I want to put up the stimulus, let them tell me what their perception is, and get a measure of brain activity. But even with all of that, we're looking at correlations of here's the brain response, the physiological response with that correlates with this particular experience. The hard problem of consciousness is how do these physiological experiences or these physiological responses cause experience or transform into and become our experience of the world? I have some examples here. So how do neural impulses become the perception of a person's face, the experience of the color red, or the feeling of a bitter cold wind? And every one of those things we can think of, there are emotional responses, right, to a person's face. There are thoughts of, is this somebody I'm working with? What are we working on? All of that comes into our mind suddenly because we look at a certain person's face. Some people in my class do this kind of, what kind of emotion does the color red cause, right? Is it an attraction kind of thing? Is there a withdrawal because of stop signs kind of thing? Do you want to wear the color red? Questions like that. And this experience of the color red, while we're not even sure we're really experiencing the same thing, we're just pointing to the same thing and calling it red, what we have is the measurement of neural impulses. And I usually use the example of that we'll get back to an olfaction, and I don't come back to the question, but you might kind of write it down somewhere so you're thinking about it. But when my mom makes sticky buns, so if your mother makes, or somebody, or you make monkey bread, I think it has a similar smell probably to sticky buns. Sticky buns, you make this kind of cinnamony, buttery, sugary, so it's moist, and then you take the dough and you roll it. You smear the moist, cinnamony, sugary stuff onto the dough, and then you roll it up and bake it. And every time I smell that smell, I'm just transformed. I just go back into my grandmother's house, and I can see her. I can see her beating on the, she used to make her own bread dough and make a whole bunch of them, and they'd be all around the house. And my grandfather, I can picture what room he's in and the room that we played in, and coming home from school and all of that. And I didn't live near my grandparents. I lived with them for a really short time. My grandmother died in 1983. So this smell can bring me back so in such a vivid way that it's incredible to me that it's actually just the flowing of potassium and sodium ions and releasing some neurotransmitters that is causing this experience. And so I hope that you have a similar kind of, wow, how do these physiological responses, how does brain chemistry and ions flowing cause or transform into experience? I feel like I went over that pretty well in the last slide and just getting at this question. So here I'm putting the picture up of the tree and what's happening at the retina, and then that translation of what's happening at the visual cortex, and that this is, so these separated hypercolumns, or these hypercolumns that are next to each other, where those orientation columns that are responding to the vertical bars that are the tree trunk, they are separated in the cortex. And so we haven't put the information back together yet, but keep coming back to this question of whether we are addressing that easy problem of consciousness, so how the physiological responses are correlating with experience, or are we really addressing the hard problem of consciousness, how those physiological responses become, how they transform into the perception of, in this case, the tree. This is another place where usually I've stopped and I've come back, but I'm just going to do this here because this is a good place to do the reminder of, well, how did we get here? Well, light was reflected. It hit those photoreceptors. The photoreceptors did the transduction. That information went through the bipolar cells, the retinal ganglion cells, and then out the optic nerve to the brain. Those subcortical structures, the lateral geniculate nucleus and the superior colliculus, received the information, as well as the hypothalamus, which I ignore. We're actually going to just take that information from the lateral geniculate nucleus and send it to the striate cortex, the primary visual cortex, which is where we've been for a little while. And now we're going to ask, where does this information go from here for higher level processing, so that we can take these features and finally put them back together, put those vertical lines back together into a tree trunk and recognize that as a tree trunk. From the visual cortex, there are two primary pathways, one going through the parietal lobes or the dorsal root. So if you think of the dorsal fin of a shark is at the back of a shark, well, that's towards our back as well, except because we are bipedal and our head goes up in this different direction. That's also at the top of the brain. So the parietal lobes, information goes up that way. For us to process where things are in our environment, I'm also going to talk briefly about, maybe this is more how do we navigate in our environment. And from the visual cortex, we also have information going through the ventral root, so the lower part of the brain, the temporal lobes, just above the temples, for us to do our object recognition, or the what pathway. As I talk about how we discovered these pathways, I always feel like this is a good place. Actually, I usually do this when I talk about the selective rearing and the kittens, but this is a good place to comment on the use of animals in research, and that if anybody would like for me to put a discussion on Blackboard or some way for you to voice your opinion about some of this animal testing. You will notice for this field, a lot of what I talk about occurred earlier in time when we really couldn't look at brain activity in humans. And so we thought this was the only way to get at this information. But I remember being in class and feeling pretty uncomfortable about mostly the kitten study. Interestingly, more so than for these monkey studies, even though they are more similar to us. As I've gotten older, that has switched, as now I feel much more uncomfortable about the monkey studies than I do about the kitten studies. But it is something that if it's making you uncomfortable at all, we can find a place where you all can discuss this, or we can have a part of that day when we have our. I still hope to have at least 1 or 2 open classes if people want to discuss ethics in animal testing. That's something you can let me know. So how did we discover these pathways? Well, we use ablation, or what's also called lesioning of the brain. And this first was conducted, this kind of research for the what and where or how pathways, where this information is going after the visual cortex. This was originally done by Ungerleider and Mishkin in 1982. And the way they would do this and the way ablation studies work is that we test the animal's capacity or their abilities. We train the animal, we measure perception, we remove some particular area of the brain, leave the rest of the brain intact, and then we retest the animal, retrain the animal to determine which of the perceptual capacities remain and which capacities or abilities were lost. And I have several pretty simplistic kind of slides that I'm going to spend a little bit of time on, and hopefully I'm going to roll through these. As the way Ungerleider and Mishkin did this study is they presented monkeys first, or trained monkeys first, on 2 tasks. One was an object discrimination problem. So the monkeys were learning that the food well, so there were 2 wells next to 2 objects, but the well that was next to, let's say, the cylinder was the well that had the food in it. So they were consistently rewarded for picking the well next to the cylinder, as opposed to, the cube or whatever. So they've learned how to discriminate between those objects. And the second was a landmark discrimination problem. So I have 2 wells, and one is next to a single landmark that says this is potentially the well, and they get rewarded for picking the one next to the landmark. So here's an example of the object discrimination task. Monkeys learn to discriminate between these 2 objects, and let's just say the food well is always underneath that rectangular solid. And so as they learn that, they can choose between the 2 objects. But then if we go in, or they went in and they removed some area of the temporal lobes, the monkeys could no longer do the object discrimination task. And so we're damaging or impairing the ventral pathway. And again, this ventral pathway through the temporal lobes is what we call our object recognition pathway. I have all of this. Again, I've tried to do this on several slides, and I usually do it with this word art, hoping that it helps people to remember this ventral pathway. But what you want to connect together from the striate cortex to the temporal lobes, it's the what pathway. It's also called the ventral route. They also, so the monkeys learned a landmark discrimination task. They could learn to choose the food well that was closest to some landmark. In this case, it is a cylinder. And so if they choose that correct well, then they get the reward of food. They're always being rewarded with food. And in this case, if the researchers went in and took out some part of the parietal lobes, now they could no longer do the landmark discrimination task. So this is the dorsal pathway through the parietal lobes. And again, just to put that all on one slide really clearly, we're going from the striate cortex, so the visual cortex, to the parietal lobes. We're calling that the where pathway because if we damage that area, this dorsal pathway, That's where we lose that, or the monkeys lose that ability to be able to do a landmark discrimination task. And for both of these, if I lose my temporal lobes and I can no longer do the object discrimination task, they can actually still do the landmark discrimination task. If I lose my parietal lobes, some area up there, and I'm no longer able to do this landmark discrimination task, I am still able to do the object discrimination task. So because of this research, Ungerleider and Mishkin proposed this idea that we have a what pathway through the ventral root going through the temporal lobes, and a where pathway going through the dorsal root through the parietal lobes. Now, in 1995, David Milner and Melvin Goodale asked the question of whether these pathways should be called the what and the where pathway, or whether these pathways should be called the what and the how pathway. So the object discrimination pathway through the temporal lobes, we're going to talk about the temporal lobes a little bit and how this is really clearly giving us our object recognition. This was actually the area of the brain that was damaged with Mr. P when he mistook his wife for a hat, when he could not recognize objects. But now we're looking at the dorsal pathway through the parietal lobes and asking, is this really about where? Or is this landmark discrimination and where things are, is that because it's so important for how we navigate through our environment? So they're asking, should the dorsal stream be called the how pathway? Because it really involves taking action with the world, which does require a where component, but it also involves the physical interaction with the objects. So this suggests that that pathway is more complicated than just seeing where landmarks or objects are. And the evidence for this comes from neuropsychology. So Milner and Goodale, from what I have read, I think it's all with this, a lot of it is with this woman DF, a particular patient who has damage to her parietal regions. But so we're going to talk a little bit now about studying these behavioral effects of brain damage in humans. And just keep in mind that this is really utilizing neuropsychology when we're looking at the behavioral effects of damage in people. And something that's important to distinguish here is a single dissociation from a double dissociation. So a dissociation in the brain is a situation where one function is absent and we've gotten that function impaired, while another function is present and it is completely maintained without function A, without the first function. But we need to distinguish single dissociations and double dissociations and what this means as far as those functions and whether or not they are truly independent of one another. I like to start this out with this example. It comes from your book, but it is just an example where, let's say we have a patient, Alice, who has brain damage to her temporal lobes, and she has difficulty naming, so that object recognition, but she has no difficulty with locating objects. At this point, we can conclude that those two functions, object recognition or naming, and being able to locate objects, that they involve different mechanisms in the brain, because we can do one without the other. They're happening in different places. But we don't know, we cannot tell if those two mechanisms are operating independently of each other, because it could be that even though I can locate without having to be able to name an object, it could be that if I want to name an object, I do need to be able to locate it, that dependency going the other direction, that might still be true. And for us to be able to say that these two mechanisms truly operate independently of each other, we need to have at least two patients. We have, I'm keeping Alice there, really tiny in our memory, that remember she has temporal lobe damage or damage to her temporal lobes. And so she cannot name, but she does not have difficulty locating. Well, we have another patient, let's say his name is Bert, and he has damage to his parietal lobes, and he has difficulty locating objects, so that's impaired, but he has no difficulty naming, so he's able to name the objects even without being able to locate them. So now that we have this double dissociation, we can conclude that those two functions involve different mechanisms and that those mechanisms are operating truly independently of one another. Okay, I'm going to come back now to that research that was done by Milner and Goodale, where they decided that maybe this isn't just a where pathway, maybe it's a how pathway. And they were working with this woman, DF, who had damage to her ventral pathway, and she was unable to match the orientation of a card that she held in her hand to different orientations of a slot. So this is the figures on the right are showing the response to a vertical slot. Okay, and A is this static, just matching the orientation. And you can see, first of all, I'm going to start with the controls. That controls that people who don't have any brain damage, we're pretty close at matching that vertical orientation, just a teeny tiny bit off sometimes. But DF, you can see that she has no idea. Sometimes she's even trying a horizontal orientation. She has no ability to match that orientation. However, when they ask her to place the card in the slot, so treat this like a mail slot and place the card through the slot. Now we look at the controls, we have a little bit of, we're a little bit off from vertical, and DF matches the controls pretty well. She's a little bit off from vertical, so being able to post the card through the slot was not a problem for her. So now we can conclude that we have one mechanism for judging orientation, but a separate mechanism in the brain for coordinating that information, the vision of the orientation with the action of actually mailing a card through the slot. If we have one mechanism for judging orientation and another mechanism for coordinating vision and action, from what we've seen so far from DF, and we're asking this question, are these mechanisms independent of each other? Can we tell from DF? And if we can't tell from DF, how do we find out? Usually I get to ask this in class and eventually someone does come up with this, oh, we need somebody who has the opposite capability, right? Who can judge the visual orientation, but they cannot accomplish the task of mailing the card through the slot, the task that is combining the vision and action. And we have seen these patients, and they have damage to the dorsal stream. So these mechanisms are clearly independent of each other. And again, this is research from Milner and Goodale, and it leads us to the question, though, I think it's a really good question of whether or not that dorsal stream, that pathway through the parietal lobes, is that truly about where, as we were kind of seeing in the monkeys, but that is also related to, and maybe we should say, especially with this research, maybe it looks like more like how do we navigate in our environment. So the dorsal pathway, they saw this pathway really as a how or an action pathway. And I'm going to stop here today. As I can see, I'm just out of time with, I hope you all did watch the very brief piece of the matrix, which isn't quite the piece I usually show, but it was just something I could find on YouTube for you all to think about. Are we really getting at this question of whether or not we are truly perceiving a world that's out there, and can we feel like these neural mechanisms are transforming into an experience of a world.